All right, people trickling in. All right, so I'm here to, I guess, scare you a little bit. it's the season. So recent extreme energy events, right, like major blackouts, near collapse of grids or regional grids, major issues relating to utility distribution, systems not being online. Those are more and more becoming winter events, right? So for a long time, we've experienced major blackouts, and they're driven by demand exceeding supply or demand exceeding the ability for wires to carry electricity during the summer, right? Because that's when the peak usually arrives, right? And the peak is the highest demand that the system is designed to accommodate. So we're seeing this happen more and more, that winter is stressing the grid. And why is that? Because of the shifting demand to winter. So what happened in Texas? I mean, does everyone remember this? Raise your hand if you remember it. Well, those silly people in Austin, Texas that have their domestic hot water heaters on the outside of their house and they're uninsulated. Yeah, they're not doing that anymore. So as we see a climate that is shifting and things are becoming more irregular and more weird, right? We're seeing the jet stream, for example, dip down into Mexico, and places in Texas will experience prolonged extreme cold temperatures. And their buildings aren't designed to do this. Their heat pumps aren't designed to work through those extremely low temperatures for a prolonged period of time. Their grid isn't set up to carry that peaking demand. Their power generation isn't set up to do that either. And they're an individual grid, right? Like Texas is alone. They're not interconnected with the rest of the country. They probably should be. So the impacts of them going down is pretty severe. And this storm, Winter Storm Uri, had an impact that is almost equivalent to the impact of Hurricane Katrina, with deaths, people freezing in their homes. So what happened exactly? I mean, in simple terms, right, the demand exceeded the supply. There are more air source heat pumps in Texas, right, as a proportion of total heating systems than almost any other place in the country. Did you know that? Yeah. And they're not really designed to operate at very low temperatures, below 20 degrees Fahrenheit. So what happens is they go from being fairly efficient in the 35-degree range or the 40-degree range to not being efficient at all. Their efficiency, or their coefficient of performance, degrades significantly as the temperature drops toward zero. And so this asymmetric loading of the grid causes some pretty serious problems. This chart is meant to kind of articulate the difference between summer peaking and winter peaking. So the red line is summer peaking, and it's sort of this diurnal effect where you get a big peak during the day, maybe it's in the afternoon, or around 5 or 6 o'clock when both commercial buildings and residential buildings are online. And then overnight, there's a drop-off. So that's pretty nice, right? Because you could actually maybe store electricity in batteries and then deploy it, and you've got a lot of solar that's online during the day. Texas actually has a ton of solar and wind. But there's time to recharge. In the winter, right, if you look at this Winter Storm Uri, this was a peaking winter event, you don't really have it. So the loads don't really drop off. It's a little bit, but not enough to make that case that you've got this ability, or this diurnal ability, to recharge a lot of energy storage and then, deploy it during the day or during the peak. So what stays in Texas doesn't, or what happens in Texas doesn't stay in Texas. It's not Vegas, right? So the top right corner image is all the natural gas pipe, right? And if Texas goes out for a prolonged period of time, eventually we lose our gas pressure in the Northeast. So, God forbid this happens again. But these issues are national, right? They could be international. We saw power prices spike when Russia invaded, Ukraine and constrained the international natural gas market. So these issues are real issues. I want to focus on the Northeast. So this, in the New York Independent System Operator, ISO, or our grid, New York has a grid operator. We can see the peaking periods, or sort of that diurnal up and down in terms of electric consumption during the polar vortex, right? Polar vortex is basically when the polar vortex falls apart and Arctic air can escape, the Arctic regions and come down into New York. And so this is happening more and more as the polar vortex weakens due to climate change. And then summer 2018. So we're still peaking, right, during the summer. The demand on the grid and local distribution and transmission and generation is still highest in the summer. So as we do more and more electrification work, right, to address climate change, as we use less and less gas and rely more and more on electricity to produce domestic hot water and space heating, and as we electrify vehicles, we're going to shift our peaks into the winter, right? And so, we asked, well, what does it look like if you shift the peak into the winter? Like, at what point does the peak, the winter peak, exceed the summer peak? And so here's a good example of converting 20% of natural gas use, 80% of current oil use in New York, using an average COP of 1.5 at the low temp, right, during that peaking period. So you might look at an air source heat pump and they say that they have a 3 or a 3.5 average COP. You have to know what the COP is during the design condition, like during the worst possible time. What is it? How much power is that system going to consume? So I'm being generous with 1.5. If we use 1.5, we establish a new winter peak. Can we afford to do this? Can we afford to, increase our entire distribution system by maybe 50%? But then you can start to see the sensitivity around COPs. So if we can achieve that peaking demand using highly efficient heat pumps, right, at 3.5 during that extreme condition, then we don't exceed the summer peak. So this is what we need to be focused on, right? Like we need to really make a concerted effort to ensure that our buildings are as tight as possible and are as efficient as possible, and I call that resource-efficient decarbonization. I'll talk a little bit about that. And this kind of shows load growth, right, as the amount of buildings electrifies over time for 1.5 COP versus 3.5 COP. And this is an extreme difference, right? There's like a big divergence here. So heating is the elephant in the room when it comes to decarbonization. It's not LED lighting or putting solar on the roof or electric vehicles. It's heating and HVAC loads and domestic hot water loads and industrial heat processes. So how are we going to shift off combustion, right, and do it in the most efficient way possible? And there's more out there than just air source heat pumps, just got to say that. And we need to store heat too. So another example of how electrification penetration across buildings and COPs are impacting demand, pretty extreme. And the value stack, right, for the marginal cost of capacity, right? So each kilowatt or megawatt that we add to our distribution system and our generation fleet and our transmission and our electricity storage system, right, the entire bulk power system, is extremely expensive. So if we can avoid growing that electric distribution system, we could save a lot of money. And where could we take that savings? We could plow it into the efficiency that I argue we have to do, right? Like we can't avoid doing this. So here's another really interesting chart showing ISO New England in 2005 and 2006, we are rarely hitting that peak. So only 1.9% of the time do we even hit the peak, right? But we're paying for this electric distribution system all year long. So this is a really asymmetric way of managing critical infrastructure, right? Like we only use it 1.9% of the time, but that's where all the cost is. It's sort of like, it's not right? Like we need to rethink this a little bit. And we need to beat this peak, right? Like the entire focus of building electrification should be focused on beating this demand peak. And we can do that with resource-efficient decarbonization. So I argue all that matters is peak demand at the design condition. So in the winter, it's when it's the coldest, or you're designing a building to withstand particular low temperatures or conditions over a prolonged period of time, the worst condition that you could design for, right? Because the building needs to withstand that, or else in the off chance that it happens, you're out of luck. We can and must do better. So here's RED. So what is it, right? It's an incremental methodology and an integrated design and planning process that phases in building transformation over time. And you can start off by identifying where, why, how, when fossil fuels are used in the building, and just understand the building. A lot of people don't know what their building is, right? There's a lot of property managers, professional property managers, that don't really know what's in the building or how energy is being used. So know the building, right? That's the first step. And then do targeted reductions in demand. Maybe improve the envelope, maybe replace the windows, insulate the roof. Target the reduction in demand so that when you do start electrifying, you've got a lower demand to electrify, meaning it's cheaper to electrify, right? And you can size systems down. Recover heat. So there's a lot of heat that is intentionally rejected from buildings or not intentionally rejected from buildings. So every time we cool, typically, right, like on a day like today, we're cooling this room. There's a lot of heat coming off of people. We're not using that heat to make domestic hot water. We're just blowing it out the top of the building. So maybe we should think about using it. So recover heat. And there's a myriad of ways to recover heat leaving the building. In the wastewater stream, right, when you take a shower and it goes down the drain and it goes out to the sewer, that water's leaving the building at 90 degrees. It passed by your body in like 3 seconds or less. Right, is that like a good utilization of heat? No, like try to get the heat back before it leaves the building and make new domestic hot water or space heat. And then target, replace specific loads, right? In a techno-economic way. So what technology do we have that is economically viable to target specific loads in a building? I'll argue that domestic hot water loads are a good target, right? That might be a place to start. And then you can phase in heating and cooling loads, right, over time. And don't try to deal with that peak yet, right? Because that's going to be very expensive. Remember, it's like less than 2-3% of the time that your building is ever hitting that peak. So try to deal with all the other loads before you address that, and think about thermal energy storage. So what does this look like when you scale it up to a neighborhood that's like this, right? Like the neighborhood that we're in. So there's a whole host of ways that you could be reducing peak, capturing excess heat, moving heat around buildings, moving heat between buildings, extracting heat from geothermal bore fields, extracting heat from the sewer, taking heat from a data center, for example, and sending it to a multifamily building. And this is the idea behind thermal energy networks, right? That we can strategically capture heat, move it around, store it where we've got space to store it for later when we need it to address that peaking condition, for example. And this is our current form of thermal storage. Jens is going to talk about how GEO is thermal. This is our current form. So this is the working storage for natural gas in the United States. We pump gas, up from gas fields in Texas and the Gulf of Mexico and Pennsylvania, and we pump it down into caverns under compression for that peaking period during the middle of the winter. So we have to convert this to electricity, right? And we have to have the ability to ship all that electric to buildings as they convert to electric. So that is why, right, doing this as efficiently as possible is absolutely critical. So here's what we need, right? We need more awareness of the value to the electric grid that geothermal, thermal energy networks, and thermal storage represent, right? This isn't rocket science, right? As we electrify buildings, we're gonna stress the grid. We have to focus on how thermal energy resources are electric capacity, right? Geothermal and thermal energy networks, they're not just non-pipe alternatives for gas, they're non-wires alternatives for the electric grid. It's really important. So those are like jargony terms for proceedings that are happening in New York State, for example, to allow utilities to make targeted investments to reduce their need to expand the electric grid or replace gas pipe. And we need to advocate, right, at state, ISO level, regional level, and at FERC, at the federal level, that these kinds of resources, thermal energy resources, are those capacity resources, and they should be treated the same way as firm capacity resources that are generating electricity or transmitting electricity or storing electricity, because it functionally does the same thing, right? People need to get this out of their head that these are two different systems. They're fully integrated systems, and they rely on each other, right? So a therm, you know, it's not any different than a kilowatt, right? Like we can even change our units of measure to make this easier to understand. We don't have to use therms anymore, or MMBTUs, or tons. We could just talk about kilowatts or megawatts, and it would change how people think about this. And we need to urge everyone to embrace this resource-efficient decarbonization approach instead of business as usual. We have to take this tactical approach to changing our buildings and how they operate, and changing our shared infrastructure that's in the street, right, with thermal energy networks, et cetera. And that's it. So Jens, we're gonna jump back to yours.
Do you want to do questions first?
No, I think we can hold them to the end. Yeah.
Okay. Yeah. So, just swap
Is it just this one?
Yep.
Great.
The full screen.
Cool. Great.
Very good. Good job, Jared. Thank you. So if you think what Jared told you is scary, I'm going to scare you a little bit more.
I didn't even talk about AI.
And because I think we are on a pathway which is not good so far, but we can change it. And that's going to be what, you know, providing a solution instead of a problem is really what I think we need to emphasize on. So we are looking at a different technology here. One of them is air source heat pumps, which obviously go down with colder source temperatures. At 0 degrees, there's simply not much heat in the air anymore. And you know, me being from Buffalo, New York, we also find out they're not really doing that great under 6 foot of snow. And so it's about resilience as well. But what we have shown over and over again, that the geosystems are providing the same COP no matter how cold it is outside, because they tap into the energy storage in the ground, something which air source don't have. And that's the important thing to emphasize about it, and it is dramatically important. Imagine I'm buying a drill rig, and I drill a borehole 1 day a year, and the rest of it is standing in my yard. Wouldn't that be the worst investment I can make? But we're doing exactly that. You know that better than I do. Most of you guys are coming from utilities. We have to create a capacity plus 19% reserve margin in order to operate it. And we don't have a choice about it because we don't want brownouts or, God forbid, blackouts. So Okay, here's number one scary movie. This is a summary from NY-GEO, which essentially is looking at how much heating energy are all the buildings in New York State going to be using. And down here is a summary on the peak day. That is 97 gigawatts. Imagine that is all done at a COP of 1 or 1.2 or 1.3. Whoa. And that is in addition to what we have as a winter peak now. That is scary. May I remind you that we only have 39 gigawatts of generating capacity, and our current winter peak is 25 gigawatts. Another way to look at this or to calculate it is to look at how much gas are we currently using for heating. So space heating is about 557 tera-BTUs, that's tera, and then the cooling is relatively small compared to it. Now you can run a very quick formula there and say how many full load heat hours do you have, et cetera, and you dial that in and you come up with about 123 gigawatts of energy you need. That is without hot water, that is without process heat, that is without car charging. This is just for heating. And this is when it kind of hits you and you're like, okay, it's going to be interesting in the next years, right? And so, a couple years ago, last year, Rory kind of challenged us and said, hey, remember the time where we made a decision to fly to the moon, and we didn't have any idea how to get there yet, but we as a nation said we got to do this. So this is the same thing. We got to figure out on how to get to the moon and how to achieve that. So geothermal, and he asked us as an industry to step up and saying, let's do this. Come up with solutions, come up with ideas. We're open to everything. And well, that obviously is one of Jared's slides. But the point being here is we got to look at this and understand that we are storing heat. Every single building I'm aware of is making enough heat to heat itself. The problem is it does it in this winter, in the summer. And we're rejecting all that heat. And then in the wintertime, we're trying to generate heat in some way or form. Why don't we store that heat? So this is the loop field in New Paltz in one day, in May. And you see, no, actually, it was a couple of days ago. And so you see here, this is heat essentially going in, this is heat going out. It reacts immediately to in and output, like an electric battery does. So some heat pumps are running in heating mode, some are cooling mode, sometimes the hot water goes on, sometimes the sun is up, sometimes there's a cloud, sometimes it's night. We have different demands, but you can see in the blue lines is the water going into the loop field, and the red line is the water going out of it. So you either inject heat or you get heat back. But it reacts exactly like a thermal battery. So every single big building I'm aware of nowadays is designed with heat pumps. And it has, because every tenant wants to control his own destiny, and then you have a cooling tower on top to get rid of heat. And when that loop is cooling down too much, you have a boiler to inject heat into the loop. But why don't we store that? All we need is essentially get rid of all that infrastructure and just put a loop field in. So we inject it into it, we store it there, we get it back 6 months later. And guess what? Developers really like it because now instead of a cooling tower, they can put solar panels on top on an additional floor and have a penthouse there and get more rent. That's really what it is. Remember Elon Musk challenging Australia and said, I'm going to fix your problem in 90 days, otherwise it's free? So this is at least it was one of the largest batteries in the world. And you can see it's the same way. You would take energy in, you put energy in, you take energy out. It reacts instantaneously. And it paid for itself within a couple of years. So here's an example. Again, Zero Place has become the kind of not only the first award-winning building of excellence, but it also streams data for the utilities, for NY-SERDA. They very granular monitored all this. And this is a typical place. In the summertime, we put a huge amount of energy in. This is one day in the summer. In the wintertime, these are 2 days actually. Some days are warmer, some days are colder. The loop field immediately reacts to input and output. It delivers, it's not dispatchable energy, but it operates that way. It gives you more when you need more. So this was the most efficient building I'm aware of. And this is at -6 degrees on a cold day in January last year. And despite that fact, 90% of the energy was heating on the peak, 15 minutes. 90%. That is the monster we're looking at. And then you ask yourself, how did this building do here? Because of that 90%, 70% came from the loop field, dispatched when you need it most. And the grid only saw that much to operate the GEO system, and it did so in a very efficient way. Keep in mind, whatever we use from the grid also ends up as heat in the building. It has nowhere else to go. It's to run the pumps and the compressor, and all that energy also ends up as heat in there. It goes directly into the heat pumps. So if you look during the day, you can see on the orange here, this is how the loop field was reacting to changing demands and delivering more when you need it more. It's ingenious. It gives you the most when you need the most, automatically. And by the way, this was the rest of the building. That was just the appliances and all the other electric loads. But the loop field was just reacting in that fashion in an ingenious way. So I want to emphasize that it's a dispatchable, and it's not dispatchable, but it acts like a dispatchable battery, like today's peaker plants do. So instead of, this was the total amount of energy, this is what the grid saw. And the fascinating portion was, the building was operating so efficiently in that way, with that GEO system, that the peak didn't occur when the heating peak was. It occurred later in the evening when people came home and turned on the dishwashers and washing machines and cooking and everything else. So it didn't even drive the peak anymore. That's how efficient it was due to this battery in the ground. So how much did that cost? Well, the whole GEO system at Zero Place was about $890,000. The loop field was about $350,000. Today it would be probably more. We're talking about 1.2 million roughly for the whole system. But we also have much more subsidies because people recognize the value of this. And the point was, I'll show you that later, how much in grid battery storage it actually saved. Now, what I'm telling you here, I'm not making up those numbers. NY-SERDA went in there, they granular monitored that system minute by minute for 1 year, or 2 years actually. They're about to publish the report. So this is all verified by the state agencies. And so it was an interesting way to look at it. I'll show you the cost numbers later. This is a study here in New York City. It's looking at the affordable housing stock here. And you can see this is the total amount of energy intensity. BTUs per square foot, I hope we're going to change that in KW down the road because it's kind of the same thing. And this is the building stock pre-2003. So you can see it's extremely energy intense. This is the newer buildings. Logically, after 2003, they use lesser energy. These are the early adopters of passive house standards here, but they're still gas heated. These are all passive house certified homes. The point is, they don't reach the passive house standard. Why? Because there are more people living in there, they have 5 computers, they have 3 Xboxes, they have 2 refrigerators, they have probably 15 TVs. Now you take on, this is the Lockport Housing Authority, this is their project in Autumn Gardens. And we put a geosystem in there. They were all electric. Here's the transformer, and they had one electric account. And they paid for all the electric and energy bills for the entire development. Perfect. We pop in a geosystem, and we see immediately how it works, right? Because we have before and after. They paid for all the electric bills. This was before. It was very efficient already, believe it or not, a 1970 building, because it's all electrified. So because it's 100% efficient instead of a 60% efficient boiler. But then we put the GEO in there, and it was right at passive house standard. That was an achievement all the other passive houses didn't achieve. And this was not weatherized. This was 1970, 50 years old. You pop in a geosystem in an affordable housing project, you have it immediately operating at passive house standard. Done. So this is actually now, you look at this from a perspective of before and after. So this is the total amount of energy used before, this is the total amount of energy used after. This is the whole building, this is not just GEO. And again, this was verified all by NY-GEO. This is the demand reduction. It went down to 45% than before. Isn't that a load curve you'd love to have as a utility? Instead of this? And oh, by the way, the peak always occurs at 6 in the morning when the sun is not shining and the wind doesn't blow. Keep that in mind. Another example. Now we're getting a little bit more courageous. So this is in New York, in Buffalo, New York, the historic Pierce Arrow building. Retrofit, 100% GEO. Heating, cooling, domestic hot water. There's no gas line going in there. This is a utility room here. This is the storage tanks for the hot water. These are the hot water heat pumps. Every single apartment has its own heat pump, 150 of them. And the performance is mind-boggling as well. Here are a couple other examples. This is Zero Place here. Of course, this is extremely efficient. This is a building, the Ciano building in Buffalo, New York, which is just code minimum plus GEO. And it exceeds the passive house standard immediately by about 30%. The bottom line is, this is again, Lockport Housing. You don't get that much more in total energy savings. The majority is really coming from the GEO system. And why? Because it can tap in this battery in the ground. So you look at single-family homes. Again, just remind everybody, 75% of the entire energy is going into the heating. And it's a long period. So keep in mind that this GEO system and the battery recharges automatically in the summertime. We're not rejecting the energy into the atmosphere again. We're sending it all down underground, and it stays there. So while GEO has always been a little bit poo-pooed in a way for the cost, because the consumer is bearing the costs, it has huge advantages as an energy storage for the grid, because whatever you get from the ground, you don't have to get from the grid. So it is really an ultimate battery. It stores all the thermal energy of the building for the whole year, and it's enough to provide everything through the winter. It doesn't need to connect to other buildings. It can be. It self-stores all the energy it needs. It stabilizes below 30 degrees because now the ground freezes, and it releases an additional huge amount of energy through the phase change. And as I showed you, it reacts immediately to input and output. Not a single kW, not a single BTU is lost. Keep in mind, the grid of the future will have the peak in the morning hours. Zero place, the data I showed you was without any solar data, but it has a 180 kW solar roof. That huge solar system did not do anything to the peak in the summer or the winter, because the peak occurred when the sun was not shining in the middle of the night or in the late evening hours in the summertime. Keep also in mind the wind isn't there necessarily. So if you look at New York State, we had 74 instances, that's once every 4 days, where the entire wind output is less than 5% of its rated capacity. So if we are putting in geothermal, we will have a minimal impact on the capacity of the grid. We can increase the load factor so significantly by using more at night and less during the day. And that way we can reduce the cost to all ratepayers. We can really make this extremely efficient. So we shouldn't look at this and how much total million BTUs we can save. We've got to look at what avoids in grid capacity, because this is really where the value is. Keep in mind, we can shave all that monster by 70% and more. And my line is, imagine you would have a battery which provides 75% of your all energy for your house. And it's coming on a 6-foot footprint, a 6-inch footprint. That's the size of a borehole. And you bury that in your front yard. And it automatically gets recharged 6 months later. And it's going to last for 6 months. We wouldn't have a grid anymore. That's what what that technology does. So I remember one of the higher-ups in New York State, one of the regulators, said to me, well, this is why we are putting in 3 gigawatts of grid storage. And oh, by the way, we're doing 6 gigawatts now. Remember the 123 gigawatts per hour, which we look at? I said, with all respect, but let me put it in perspective. All the battery capacity you want to put in for billions of dollars will last you 4 minutes on the peak day in the winter. So keep in mind, we don't need to recharge this. This recharges automatically in the summertime. So we don't need any kind of generators for that. We don't need the grid capacity to recharge all the batteries. We don't depend on whether the sun shines or the wind blows. And the loop field is rated for at least 200 years, life expectancy. It doesn't degrade like an electric battery does. So if we would actually put this in, we would eliminate the gas distribution network, which is corroded anyway, and we need to fix it somehow. But why do we keep 2 energy networks going? Focus on one and make it right. It would have minimal impact on the grid capacity. We increase the load factor, we reduce all the costs. So here's some cost examples from Zero Place. The current cost of grid capacity is about $567 per kilowatt hour. That's how the average installation costs for a grid battery in New York State was 2 years ago. On the peak day, it delivered 1,706 kW, kilowatt hours. That would have cost us about $1 million to put this into the grid. Remember when I said the loop field costs $350,000 and everybody's complaining it's so expensive? Now you can say, what about if this is for one day? Well, what about the next day? What about the week? What about a month? What about if there's no sun shining for like 2 weeks, a month, because we have a cloud cover? Well, this is how much grid battery storage we avoided. Now, this is probably, the value is probably somewhere in between here, because we cannot always assume that our solar panels are recharging every single day in the middle of the winter. So now you go back and say, look at the residential systems. So these are 10 systems in Buffalo, New York. And during the peak time, it extracted about close to 10 kW from the loop field. That's how much it avoided in the grid. And again, this is a single family home where the loop field is going to cost you 15 grand, or the borehole. But it avoided, essentially, on a peak day, about $100,000 worth of grid storage capacity. In one day, it paid for itself. So part of our metrics, I think, is wrong, because what we're looking at is the total amount of energy savings. How much does it save us for the year? We're not looking how much peak does it shave. This is where your costs are, because we have to put in this infrastructure and this capacity for it. So right now, even with today's program, we're just incentivizing the total amount of energy savings or the total amount of emission savings. But we got to change our thinking here to say it's really about the peak. So only GEO heat pumps can actually provide that storage component. Keep in mind that we're all looking at the projections, and even the independent system operators agree with this. They're saying we don't have any technology which can actually produce dispatchable energy, renewable, at scale. We got nothing. This is the only thing we got so far. Without implementing this technology, our entire dream about a renewable grid will go away. I'm open for any other suggestion how we can come up with energy storage on that scale. Challenge me, please. So, at the end, GEO is cheaper to install than any other technology today, thanks to all the incentives in the Inflation Reduction Act. All the other incentives are going away for air source heat pumps because they're part of the problem, they're not part of the solution because they don't have the energy storage component. We can operate this much cheaper and maintain it much cheaper. And so if you compare that with the current distribution system of energy, we really have to focus on one network, which is electrification, but we have to do it right. It is not just sitting there saying, we create a huge demand and then we reply to it. And this is NY-GEO, last slide here. We are actually commissioning the GEO systems for the hot water there as we speak. We can, if you would have told me 5 years ago we're doing this in the middle of New York City in affordable housing projects like this, I would have laughed about you. This is where we are today. We're tapping into the ground as a battery, and believe it or not, the performance data we have so far exceed our expectations by over 100%. This is the technology of the future. Thus far, it's the only way forward. Thank you very much.
So for those of you who are new to this conference, we are the only conference that I know that records all of the comments and questions. So if you have a question for Jens or Jared, I will come to you and then stuff this in your face. So please tell your name and your question, and make it a question, not a comment, unless if it's a good one. And then you guys can point me in a direction.
Sure. So let me ask you around the room, who's working for a utility? Or who's working for an energy sector? Okay, about half of it, maybe a third of it, very good. What is your solution? Okay, no more hands up, great. But that's really what we have to have that conversation. We have the technology to avoid that. We have the technology to store that energy. It's working, it's verified by state agencies. We're not making this up.
I think you can do better.
We can do better? You have a mic?
Well, I actually have a question. I have some modeling software that I think will show you can do better. One thing you don't mention, how you can integrate solar PV into your system. You're just passively accepting it if it's there. So that's just one example. And I guess I don't quite understand your system in terms of, say, I think it was the new pulse. And when you refer to thermal storage, are you talking about thermal storage in terms of extracting heat from the ground or actively injecting thermal energy into the ground on, say, a warm day?
That's what we're talking about, indeed. So because you saw how much we're injecting as much heat into the ground in the summertime as we take out in the wintertime.
Injecting it by taking from the air?
No, we're injecting it. So the way GEO works is it's cooling down the building, and instead of having a condenser outside where we inject the thermal energy into the atmosphere, we're sending it all underground.
This is in the summer.
So yeah, in the summer, we are essentially heating up the ground to about 80 degrees roughly. And in the wintertime, we take all that heat out of the rock. We inject it there before, and we're going down to about 40.
But in the northern part of the state, you don't have that much cooling.
No. Believe it or not, every single multifamily building, even in Buffalo, New York, is cooling dominated. The internal gains of those buildings, with all the people, with all the density in there, and all the appliances and everything else, all ends up as heat in the building. Every single, heating is not the problem, cooling is. So this is why we emphasize we want to make the hot water all year long so we can cool the loop field in the summertime. We're definitely rejecting much more energy, and I show that in the next hour. We're rejecting more energy into the ground than we're taking out of the ground.
And just to add to this, that effect is exacerbated in large commercial buildings. So if you come to New York City during the winter, right, you see plumes of steam rising from buildings, and that's often that cooling towers are running even in February on a sunny day.
Yeah. So what we're saying is, don't get rid of the heat. Don't reject it in the atmosphere. It's valuable. We need it 6 months later.
We could talk later. I have
Sure.
a question in upstate, if that's the case. I would believe that downstate.
We're measuring upstate. We're streaming live data on about 1,000 geosystems now to our service. Every single one rejects more heat into the ground than we're taking out.
Okay, you can ask more questions after.
Doctor, my name is Gino DeRezzi from Ground Heat in Canada. Now that you have some utilities here, you did a really good presentation on today as well, but on the benefits of reducing the kilowatt as opposed to the utility as to fabricating and the grid costs. Just very briefly, thank you.
The benefits to the utilities. Well, you know, I think we have to keep in mind that utilities are banks. They finance public infrastructure. And the more infrastructure they finance, essentially the more they can rate base it. So there's a little bit of a conflict there, but then on the other side, we have to be realistic. We want this all to work. If you don't see that this is a huge opportunity for utilities, and it's not a joke when I tell them, what's wrong with the idea of drilling a hole, extracting the energy out of it, and then selling to the end consumer per energy unit? Isn't that what the utility does in the gas sector? And I understand you don't drill the holes. You just have the distribution network there. But the important thing is really to understand that this might be, it's really not that much different. You invest into those infrastructures, and you have open ears now when this technologies you're putting in are actually, if you want to rate base them. I think the regulators are looking for that. It's just a mindset difference. It's as Jared always says, it's a psychology problem.
Yeah,
we need to change our thinking.
A utility is only as good as its public service law or the regulatory regime that controls it, right? A utility doesn't really care how it acts or lives, right? It's sort of a robot, and we could feed it software, and that's the regulatory regime. So if we could change how the regulator sees capacity, right, then we can change how the utility acts. And there's proceedings in New York State, for example, that are ongoing that are aimed directly at that specific task to change the regulatory regime. The Utility Thermal Energy Networks and Jobs Act, right, that was sort of like a shot in the arm to kind of change how we think about utilities. Maybe there are also thermal energy utilities, right? It's not done. We still need a regulatory regime to see the value to the capacity value of these systems, right? So we have to change that. That's first and foremost. And Jens was saying earlier, it's like, I think the utility is the target for this industry. And I'm like, I think it's the regulator. So we got to be talking to the regulator and shaping those processes and continuing to do it. And if the process doesn't shake out appropriately, well, then we probably need legislation to force it.
I mean, you run the wire to the customer, right? You supply the energy infrastructure. Why can't you just run the plastic pipe from the borehole in front of the house to the customer and actually put the borehole in and provide the energy needed?
I mean, the part of the other issue too, and we're talking about, opposing interests here. There are a lot of interests that would rather see this conversation go away entirely, right? We can't electrify. So just be aware of that, right, when these conversations are coming up. And sometimes I'll hear from, for example, environmentalists that will say that our conversation here is destructive. Don't talk about this issue. But someone's gonna talk about it, and it's the opposing side. So we need to be ready to say, wait, there's an alternative option here. We don't have to blow up the grid. We don't have to do crazy things here. We can actually think strategically about this and get everybody to the table. We're not getting the gas interests to the table, right? They're gonna be opposed to this because this is supposed to put them out of business. We're never getting them to the table unless they start to change their business model and invest in this and think that they can make more money at this than, drilling and shipping gas. I don't know if that's gonna happen, but we have to get everyone on the same table, and we can't have an air source heat pump versus a geothermal heat pump fight, right, which has been going on for the past couple years, right? We can't do that. We need to talk about what the biggest problem is, and it's this idea that for less than 3% of the time, we have to deliver this massive amount of electricity and get it to everybody's door, while at the same time do that for vehicles and heavy industry, and now we're gonna add AI to the picture. So that's our most critical issue. It's beating this peak, right? And we have to just keep hammering that until people actually understand what it means physically in our environment, right, in our built environment.
So yeah, we clearly have to simply change our thinking. That's what it is. I mean, remember the times where, we had catalytic we had cars without catalytic converters, and then we complained about that it adds like $1,200 to each car because now we're putting that in, and now we're going the electric route. Can you imagine a car without a catalytic converter nowadays? Remember in New York City 30 years ago, 40 years ago, how bad it was? And it's the same with the heating. We used to heat with wood, and now and then we heat with coal, and then we heat with oil, and then we put gas in, and Now we have a better and much more, it doesn't make sense anymore. Once we have that technology nailed down and we know how to do it and it's working and we have the results one after another, that's where we're going. So we ask everybody for their help on the utility side. This will be your future business model. There's no way to avoid it. Otherwise, tell me how else you're going to do this entire load and satisfy it without burning anything, because that's off the table now. Yes. Yeah.
Back to a technical question. During the summer, right, for a typical loop system, is there a cap on how much energy you can store from what's injected into the ground, right? And at what point does it cap out?
Yeah, I mean, you like I said, all our systems are designed for cooling because the cooling load is more than the heating load. But we don't account for it. That's why we don't know it. We reject it just into the atmosphere. And if you actually put the hot water load on it, it kind of balances itself out. And keep in mind that the compressor heat in the wintertime helps you because what you draw from the grid also ends up as heat, as a COP of 1 in the building. But in the summertime, it needs to also be rejected into the loop field. So you need to extract lesser heat energy, but more cooling energy needs to go in because of the compressor heat now needs to be rejected as well. So that's important to understand. And yes, you're absolutely correct. How do we deal with it? We just make sure we make it large enough. And there are some models now to say, hey, can I have a big radiator on the roof, which I run in the middle of the summer at night when it's 70 degrees outside, and can I reject and cool the loop field then when I have excess amount of energy? And those are viable models. We're looking at that as well. But no, all our loop fields need to be large enough to deal with the heat rejection, and you got to watch out that they don't heat up over the years.
Yeah, you could overheat the ground and
Yes.
diminish your ability to cool.
So we've
Right.
seen loop fields which have been installed many years ago, and now suddenly, and the system weren't as efficient, and they're not taking enough heat out of the ground in the wintertime, which are not balanced well. And then it overheats. And people have done in the past that with snow melting for free. My claim to fame always is, I give you all your hot water making equipment for free. Do you want this, Mr. Developer? The answer always is yes. Why? Because now I can cool my loop field 24/7, 365 a year. And by that, I can balance it. So I make it smaller. I save boreholes by putting an additional thermal demand on it during the summertime.
So this
Make sense?
issue of imbalance is also solvable if you make the system bigger or add additional buildings to it, right? So that's the concept of the thermal energy network, where if you create a bigger load diversity being served by that network, right, you can better balance systems and direct heat to where it needs to be. Boreholes aren't the only way. I mean, we're at a GEO conference, and it's controversial to say that, but boreholes aren't the only way to get heat into a system, store heat, or reject heat from a system. So I talked about the marginal cost of capacity. So for every kilowatt of incremental capacity that you're either adding to a system, right, in order to reach that demand, that exists for these systems too, for GEO. So could I not drill an extra borehole, save some money, and do something like a tank, right? In Germany, they pair solar thermal with geothermal, often. They also dig up football pitches, and they insulate underneath, fill it with gravel and water, and that's a giant thermal storage tank. Or they do above-ground tanks. There's a giant thermal storage tank that was just built by Consigli at the University of New Hampshire. So, you know, we can do this, we know how to do it, and we can figure out what's that marginal cost of that additional capacity for all of these different technologies and figure out how to dispatch that or deploy that to optimize the cost of a system.
Okay, so we're at time, but thanks to Jens and Jared They will stay after and answer all your other questions. We have a 30-minute break, but come back for Heat Pumps 101 with Water Furnace.
Thank you. Thank you.